So now looking at a machine with the von Neumann architecture, this is what it would look like. You'd have a control unit, processing unit, and a memory unit. Then you have your inputs and your outputs. And the control unit is basically where you point to, okay, this is the part, this is the number of the instruction that I'm going to use. And the way that it goes is that you have an instruction pointer that basically fetches the input, and your input is somewhere in memory, and that memory basically is that input is basically fed into a processing unit, which is your actual processor, and then the processor computes some things and stores stuff to memory, right? So it returns stuff to memory, and this is basically your output. But you can have also the control unit for basically having an output, and we are going to talk about this a bit later. For example, when you have things that are jump to statements, for example, where you basically change, you just change the IP right away. So when I was talking, and when I showed the picture of the stack, I took that there's the instruction set architecture and there's the microarchitecture. And the instruction set architecture is basically what we call today the x86 architecture, the ARM architecture, and so on. And these are the interface to which you provide to programmers. And back in the old days, these were the only way you could program a machine, computer. You needed to basically write assembly code. There were no C, there were no programming languages, and these were your programming languages. But then we developed compilers, we developed operating systems, and we developed programming languages as abstraction layers on top of the ISA. Underneath the ISA, there's the implementation of the ISA. And let's call it ISA from now on, instruction set architecture. And the actual implementation is the microarchitecture. And the microarchitecture is more on on how you're going to implement the instructions that you define in the instruction set. So how do you implement the add? Do you have an add that basically, do you have a register, basically place in memory, to which you always and then add that has just one operand, one input. So, and you always add whatever. So you have add, and as a parameter you take just one parameter. And when you call the command add, you'll just add it to a register that is predefined. That's one way of doing it. The other way would be to have an add and to have all results stored in a certain place that you have defined already, but you have the add, and then you have two different inputs, two different parameters. So add x and y, and then x and y gets added and gets stored there. Another way to design an add is basically to say add and have x, y, and store the results in z. So you have three parameters. So these are all ways to implement the command add. And these are the microarchitectural stuff. How do you implement these things? And they also have a lot of other things that we're going to talk about later, like pipelining and out-of-order execution, and these things. And it is very important to say that the ISA might be much more sustainable as a maintained, because this is sort of your programming language, and you do not want to change your programming interfaces too often. But the way you implement things on the microarchitecture might change. But at the end of the day, it's just an add to you as a user. And these are two definitions of ISAs that you can take a look at, because we're not going to read definitions today, but just for you to look at them. So this is sort of a rehash of what I just said. Sorry. So I'm also going to skip that. It's just explained. This is a nice analogy that also I found, that the difference between an ISA and a microarchitecture, this should be micro, not a U architecture, it's a microarchitecture, is that ISA is like the gas pedal, the interface for you to accelerate, while the microarchitecture is the implementation of the engine, how the engine works. To map that to cars, I mean, all cars in Sweden, or most cars in Sweden, can be viewed as uh, having almost the same architecture. If they are manual, they have the same architecture. You have the gas pedal on the right. You have the brakes in between. You have the clutches on the left, right? I mean, for a manual car, this is a standard, and you as a driver, you sit on the left hand side. So suppose now I have my Skoda Octavia 1998, and you have your Porsche. Okay, you have a Porsche Cayenne or a Porsche Carrera. Both of us have the same gas pedal, as in, well, we have the rubber thing, right? Maybe yours is a bit more fancy, but pressing on the same gas pedal does not give us the same acceleration. So while I might have just like pushed my gas pedal until it hit the floor, and you just touched your Porsche Cayenne's gas pedal, you will make me eat dust, right? I mean, so this is the internal implementation of the microarchitecture. This is the microarchitecture now. So, although we might have the same gas pedal, we do not have the same speed and we do not have the same performance. And this is sort of important to understand, because when we basically get a new Intel chip, you get a new engine, but you might not even change the ISA, which you do not change actually. It's x86 and it has been there since forever. You add a few things, you remove a few things, but it has been consistent almost for the past 10 years at least. Uh, and as long as the microarchitecture supports what the ISA says, then it's all fine. As long as we both have the same car, the same interface to the gas pedal, nobody cares. Okay? And to basically talk about different ISOs, then that would be, for example, the manual car versus an automatic car. Or in an automatic car, you just have two pedals, the right one for your gas, the left one for your brakes, and that's it. There's no third pedal. So this is a different architecture, a microarchitecture now. And a completely different microarchitecture that just baffles everyone is to go and drive in Britain, where you have the driver sitting on the right hand side, on the wrong side, and you have the gas pedal on the left, and you have your clutches on the right, and you have your brakes in between, which basically is, well, just counterintuitive in every sense to most people who have been driving the right way. So that's a completely different microarchitecture, for example. And, well, the British people and the Australians will tell you that this is the best architecture in the world. You're driving on the wrong hand side of the world, but yeah, I mean, this is it. So you get these fans about different architectures as you would get them on the right versus left hand driving. Okay? And microarchitectures usually change faster than ISAs, and this is exactly the same for cars. The interface to your gas has not changed for the past. I've been driving. I mean, the oldest car I drove was a 1982 Czechoslovakian car, and it has exactly the same interface, which is basically the gas pedal. Okay, so it has been 30 years, but that Czech car is very different. It was from Czechoslovakia back then. It's very different from my Czech car, which is a Skoda now. Okay, so there is a significant difference between both of them. And it's the same with microarchitectures. You change the microarchitecture, but you try to keep the ISA constant. So now we talking about the ISAs. An ISA is basically defines the following things, which is basically the instructions that are going to run on the processor, the memory, how the memory mapping looks like, and how large is the memory. So is it 8 bits? Is it 16 bits? Is it 64 bits? Is it 128 bits? I mean, how does the memory look like? It defines things such as the interrupts and the exceptions, which are very important for you as an operating systems developer. Defines things such as the access control. Do you have the kernel mode bit, which not all processors have actually, but operating systems rely on them to a huge extent. I mean, at least the ones we have been studying. Uh, I/O. How do you basically compact I/O? Thread management, because threading is has two levels. One of them is your application, but the other part of threading is basically the management of the threads on the actual core processors. Power and thermal management, which is again touches upon operating systems. We're not going to cover that in the core course. It's support for multi-threading, it's support for virtualization, and these things.